All right, so we are. We're now live. I am a couple minutes early this morning, beating my normal few minutes late. You know, it's never too late to start making positive changes, right? Let's see. Just checking to see if we got any clutch business going down. Oh, there we go. Yep. One piece of business. Well, that you should be aware of if you're not. Is our lab, first lab exercise and quiz is due today. And as always, all assignments in this class are due at 11:59. Excuse me. If you're one of those procrastinators who likes to wait to the last possible minute, you should know that that the quiz, if you haven't looked at it yet, the lab quiz is 30 minutes long. And if you begin taking the quiz at like 11:50, you're only gonna have 9 minutes to take it, because at 11:59, that's when it's due. So however much progress you've made, that's when the quiz closes down. Oh, is it not due till tomorrow? Am I a day early? All these things are possible. Let me take a look. Lecture. Oh, lab duties. Oh my goodness, Jen. Not Jen. Susan. Sorry, yes. Sorry. Oh my gosh. My apologies to everyone whom I just gave a heart attack to. It's due tomorrow. Oh wow, that is the world's smallest. It is. You are all right. Sorry, you are all right. Yes, homework 1 is due tonight. That's where my brain messed up. It is due tomorrow. Today, homework 1 is due. Homework 1 is due today. Okay, yes, that is. That is the correct business. Yes. My my apologies to everyone who, for a split second, thought that they had far less time than they do. Labs 1 and 2 due tomorrow. Yes. Sorry. I'm sorry. I'd like to say it's early. It's 1:20. You know, it's been a Monday for me. We were cleaning dog urine out of the couch today, which was tons of fun. Yeah, it's been a morning. But the baby's asleep, I'm in class, I get to hang out with adults online and talk about chemistry. So that's a good afternoon for me. If you haven't, our mixtape today is Born to Fuel study time. It is highlighting the music of the Misfits. If you are unaware, haven't ever heard them before, they're excellent study music. It's B movie horror sung like 50s era love ballads. It's like nothing else, like no one else. Dude, fish are the way to go. I'm pretty sure that that our current dog, whom we love, like I genuinely love this animal, but I think it's going to be the last mammal that we ever bring into our home. He's he's a labradoodle, but I think he was like half. I think one of his parents were a labradoodle, and the other one was a poodle. So he's in the doodle category, but I don't think he's like spot on labradoodle. I think he's a labradoodle crossed back with another poodle, so he's more poodle than lab. He's a sweetheart. His name is Rigby, named after Rigby of the regular show. And he he looks really ugly. He looks like a Muppet that Jim Henson made in a creative flourish, and then was like, nah, I'm not going to use this. He literally looks like something from the Dark Crystal. So he's pretty weird. We love him. But he greeted us with a fun mess this morning. Anyways, enough about me. Let's talk about chemistry. We are technically done with chapter 2. However, I said I'd like to get a little bit more, at least one more rep in with density. So let's do a, Carolyn, I totally can and will. He's a very strange animal. Maybe I might sneak him into maybe one of our posts. I mean, he's cute in a fashion. If you look at him, you probably think he's cute, but I look at him and I think you look like a failed experiment. But here's the point of our dog, though, is you can't judge a book by its cover because he's the sweetest dog, and I love him to death. He's like the kind of person you date because they're a ton of fun, not because they look attractive. Because he doesn't to me, but I love him. Anyways, let's wrap up chapter 2 with another density problem, and I wanted to do a density problem that's kind of next level, something that I would call exam caliber, a thing that Peyton, that's awesome, especially when you have guests over. He can sneeze but doesn't know how to sit. Well, maybe our dogs can get together and teach each other the things that they're lacking, because our dog definitely does not sneeze on command. Okay, so let's dive into this example. Hang on, I just need to check to make sure I got the right. Oops. The right density here. Yep, there we go. All right. So the density of aluminum metal is 2.701 grams per milliliter. Let me just make sure that. There we go. What volume? Actually, hang on. Let me rephrase that. What is the volume in liters of 682 grams of aluminum? All right. Now, first thing you got to do when you are solving a problem is you need to identify what you're trying to find, right? That is job number one. And here in this problem, we're trying to find the volume in liters, all right? We're trying to find the volume in liters. We're asked here, what volume? What is the volume in liters? All right. Now, once you know what you're trying to find, you want to identify what you have been given, all right? These are the tools that we're going to use to solve this problem. One thing that I see that we're given is we're given a mass, right? We know that the mass of aluminum is 682 grams, all right? The second thing we're given here is we're told the density of aluminum is 2.701 grams per milliliter. Now here, I want to stop, all right? I want to pause here because we've been given density, all right? We've been told the density of aluminum right up here. And density has an equation associated with it. Every time you're given a quantity that has a mathematical equation connected to it, you want to write out that equation as part of your givens. The density of aluminum, the equation for density is equal to mass over volume. All right? And here's where this pays off. We've been asked to find the volume, right? We want to find volume, and here it is in the denominator of this expression. When you look at what we're given the mass, we're given the density, so we can use this equation to solve this problem. It's given us a roadmap to solving this problem, all right? So the first thing we got to do is we need to solve for volume, right? That's what we're trying to find. We need to isolate it on one side of the equation. And right now you'll notice it's in the denominator. All right, so if we're gonna solve for volume, we need to remove volume from a denominator. We need to liberate it from that denominator, and you do that by multiplying both sides of your equation by the volume of aluminum. Here, volume will cancel. All right, leaving us with an expression, the volume of aluminum times the density of aluminum is equal to the mass of aluminum. All right, we still need to isolate volume on one side of our equation, so we divide both sides by volume, not by volume, by density. Here density cancels, and we get a new expression, the volume of aluminum is equal to the mass of aluminum divided by our density. We know what our mass and density of aluminum are, so here we can plug these two things in. All right, I'm going to open up a new slide. So here we have we have volume, just rewriting this here, is equal to mass over density, and plug in our value for mass. It's 682 grams, and then our value for volume 2.7. Our value for density. There we go. 2.701 grams per milliliter. All right, now we divide one by the other. 682 divided by 2.701. And my calculator is telling me that the answer is 252.4990. All right. But let's look at our sig figs. We have a number in our numerator that has 3 significant figures. We have a number in our denominator that has 4, and we know that when we're multiplying and dividing, we have to roll with whichever has fewer. So we're allowed to keep 3 significant digits. 4 is going to round down, right? 4 rounds down. So our volume, the volume that aluminum occupies, is 252. Now the question is 252 what? When you look at our units, here grams and grams cancel. So the unit we're left with is milliliters, right? But if you go back and check the original problem, we were asked to find the volume of our aluminum in liters. So we actually have one last step. We need to convert from milliliters to liters. And milli means 10 to the negative 3, so 1 milliliter is 10 to the negative 3rd liters. All right, so now milliliters cancel milliliters. You multiply your volume, your 252 times 10 to the negative 3rd, and we get the volume that our sample of aluminum occupies is 0.252 liters. And this is our final answer. All right, so this is another example of a kind of a harder problem. You'll notice that it had both, we had to find the volume, which was in the denominator, right? So a little more algebra. And it also had a unit conversion thrown in there. It gave us our density in grams per milliliters, but then asked us for a volume in liters. So it kind of pulled together several different things, and of course rules for sig figs. This is a problem that's definitely worthy of the exam. You'll see examples very similar to this one, actually in the extra credit homework, which is not homework, the extra credit assignment, which is up on Canvas right now. Cool. All right, so I wanted to do just kind of a harder density example. This is an example of one. And with that, we'll bring chapter 2 to a close and move on to chapter 3. Let's. Sorry, just saw myself in the replay ducking down. I'm not trying to hide from you. I was just moving a cord away from my chair so I don't run over it. All right, chapter 3. Chapter 3, we are going to dive into atomic structure and the periodic table. All right, so when you think of an atom, all right, you probably think of let's see, question from the extra credit assignment. Yes, yeah. Say, let's let's hit it in office hours, or at the end of lecture. At the very end, I'll hang out for a few minutes. We can get some kind of random various problems from various places, but let's stay on course with lecture for now. Okay, so atoms are comprised of, there's 3 fundamental, what we call subatomic particles. Totally. Subatomic particles. All right, these are the three dudes that make up the atom. All right, and I'm sure you're familiar. There are protons, neutrons, and electrons. And just to make sure we're all on the same page, protons are symbolized with a capital P, lowercase p. Neutrons, lowercase n. Electrons, lowercase e. All right? Protons, as you can see, are positive. They have positive charges. Neutrons have no charge, and electrons have negative charges. Right? So neutrons are neutral, they have no charge, and protons have a positive charge. All right, and when you think of an atom, there is something called the nucleus, which is where all the protons and neutrons hang out. It's where most of the mass associated with an atom is, in the nucleus. And then around the nucleus, electrons are spinning around and buzzing like little tiny negative bees. All right. So this part in here, where all the protons and neutrons are, this is called the nucleus. All right, and because protons and neutrons are the subatomic particles, that's like particle and Squirtle had a baby. Because they're the particles in the nucleus, we call these generically nucleons. All right, so when you hear the word nucleon, it's talking about protons and neutrons together. So nucleons is just a generic term for anything found in the nucleus. Electrons aren't found there. So it's nucleons are the protons and neutrons, and electrons are just electrons. It's kind of like in my family. So I'm like the oldest, and then there's like my sister, and then I have two youngest brothers. And for whatever reason, I was Josh. My sister was Rebecca, and then my two younger brothers were called the boys. They were just lumped together. And that's kind of what happened with nucleons, is they're both kind of together, they're in the same space, so we just call them the nucleons. They don't get, we don't use their names for them. You know, my mom would say, hey, Josh, go get Rebecca, or hey, Josh, go get the boys, but it was never, they were never differentiated from each other. So anyways, that's what's going on with nucleons. Now, when you look at the periodic table, so here I'm going to recreate everyone's favorite element, silicon. If you look it up on the periodic table, you'll see a number up top, that's 14, and a number down below, 28.09. This number up at the top, this is called the atomic number. All right? This is the atomic number, which is given the symbol of a capital Z. So whenever you see a capital Z written, it's referring to the atomic number. And the atomic number is equal to the number of protons that an element has. All right, so you can look up on the periodic table, look at any element, and the periodic table will tell you the number of protons because it's written on the periodic table above every single elemental symbol. Pretty nifty. All right, something to keep in mind is, as long as we're talking about a neutral element, right? And what do I mean by neutral? Do I mean that it doesn't It doesn't engage in warfare. No, not at all. A neutral means that it's not positive or negative. It doesn't have more positive charges or negative charges. It's neutral. They're in balance. For a neutral element, it's worth noting that the number of protons will always equal the number of electrons, right? Because if it's neutral, the number of positives and the number of negatives are in balance, right? They're balanced together, so they'll always be equal to each other. So the atomic number technically is only telling you about protons, but if we're talking about neutral elements, it also gives you the number of electrons. Silicon, as a neutral element, will have 14 protons and 14 electrons. One thing that is wholly missing from the periodic table are neutrons, all right? The periodic table turns out that the periodic table has no information on the number of neutrons that an element has. You can find this nowhere on the periodic table. All right? And so you need additional information not found on the periodic table if you want to know how many neutrons are present. And you find that additional information by looking at something called the mass number. All right? Now, the mass number is abbreviated with a capital A. All right? That's the mass number. And the mass number, A, is equal to the number of protons plus the number of neutrons. All right? In other words, it equals the number of nucleons present. All right? So the mass number is equal to the number of nucleons present. All right? Now, to have a complete understanding of how many subatomic particles are present in an element, you need to know both the atomic number and the mass number. The atomic number gives you the protons and electrons if it's neutral, and the mass number will give you the sum of the protons and neutrons, so you can solve for the neutron count by itself. All right. Now, here's how you use the mass number and the atomic number to depict. So there's a nomenclature for how you write these things. All right, and there's three ways to write out write all the information together. So you can write the elemental symbol with, to the left of the molecule, you have A superscripted and Z subscripted. That's one way to write it. Or you can write the elemental symbol out with a dash followed by the mass number, or you can write out the element's entire name with a dash followed by the mass number. All right, these are the three different ways to depict, or to include, I should say, the mass number with the other information about the element. So, whoops, whoa, getting crazy. There's my eraser. So, for example, you could run into problems like the following. Determine, all right, and if this kind of way of depicting, like me writing the element with A and Z and all that stuff, if that seems a little abstract, just hang with me. Let's do this problem. It'll help it make a little more sense. All right, so let's do the following example. Determine the number of protons, neutrons, and electrons in the following. All right. Let's start with all right. So here we've been given an element, sodium, and we have been given both its mass number and its atomic number. Now, when it comes to determining the number of protons, you always look at the atomic number. All right. The atomic number will be subscripted to the left, and that is the number of protons in this atom. There are 11 protons. And remember, in a neutral element, and you can see there's no charge here associated with the sodium, there will be the same number of electrons. All right, 11 protons, 11 electrons. You get both of those from the mass number. Now to find the number of, I'm sorry, I said mass number, atomic number for protons and electrons. To find the number of neutrons, we have to look at the mass number. And it's a very common mistake to go, oh, the mass number is the number of neutrons. That is not correct, all right? Remember that the mass number, 23, for this molecule, is equal to the number of protons plus the number of neutrons. The neutron count isn't equal to the mass number. We actually have to solve that. 23 is equal to 11 plus the number of neutrons. You subtract 11 from both sides and you find that our neutron count for this molecule, it's not molecule, excuse me, atom, is 12. So 11 protons, 11 electrons, and 12 neutrons in sodium 23. Susan. Oops. The periodic table puts the atomic number, which is protons, above each element. So you can look up the atomic number by looking at the periodic table, but you can't find the mass number anywhere. The mass number has to be given to you. So you can always look up the atomic number, but you have to be given the mass number. All right, let's do another example here. Same problem, determine the number of protons, neutrons, and electrons in the atom F19. All right, now here for F19, this number, remember, is this number right here. It's the mass number. 19 is equal to the number of protons plus the number of neutrons. All right? This is not enough information to solve anything. We need to know how many protons are in this molecule before we can use it to find the number of neutrons. And for that, you actually have to turn to the periodic table. All right, you have to find fluorine on the periodic table so we can figure out what its mass number is. And fluorine, sorry, not a mass number, to figure out what its atomic number is. Fluorine is number 9. It has an atomic number of 9. Now, we can plug that in because we know that's our proton count and find the number of neutrons. So for F19, we have 10 neutrons, 9 protons, right, because that's our atomic number, and 9 electrons, because for neutral elements, protons and electrons are the same, present in the same quantities. All right, so that is how you use this nomenclature to find it. Let's do one more. Same problem, but for this, let's look up the atom. Gold 197. Whoa! 197. That is a huge mass number. Again, remember, or here, actually, over here, we wrote out the entire element's name, gold, and 197 is our mass number. 197 is equal to the sum of our nucleons, protons, together with neutrons. All right, now when you look up the atomic number for gold, it's way down there. There are 79 protons present in one atom of gold, if you can believe it. So this is equal to 79 plus our neutron count. All right. So now we need to find our number of neutrons. Take 197 and subtract 79. So there are 118 neutrons present in gold 197. There are 79 protons, because that's our atomic number. And because this is a neutral element, there must be the same number of electrons. All right, so that is our neutron count, proton count, and electron count for gold 197, and that is how you use kind of these three ways of writing out an element, but including the information of its mass number. All right, so now the reason why the periodic table doesn't include any information about neutrons, the reason why it's so proton focused, is because the proton count in an atom determines that element's identity. All right, gold is the element with 79 protons. Silicon is the element with 14 protons. Fluorine is the element with 9 protons. The number of protons determines the type of element that an atom is. All right, the identity and the proton count are inextricably tied. All right, and the reason why that the information about neutrons is omitted. Let's see. In case someone is still searching for gold. Oh, yes. Sorry, Jen. Thank you. Yes, gold is AU. Yeah. It's because gold, the word starts with an A and a U. No, it's because of Latin stuff. The Latin name for gold, which I don't know, but it has an AU in it. I know that much. All right, so an element is what the type of element every specific atom is determined by its proton count. But the amount of neutrons present in that nucleus can be different for atoms of the same element. All right, this idea, this concept, that atoms of the same element can have different neutron counts. This is known. These are known as isotopes. All right, isotopes are. Oh, nice. Say, you taught me something today. How's that for role reversal? Gold in Latin is aureus, which has an AU in it, turns out. I'm learning chemistry today, which makes it a good day. All right, now an isotope. Isotopes are atoms of the same element with different neutron counts. So they're basically atoms with the same element. That's saying atoms with the same number of protons, but have varying numbers of neutrons. All right, that is the definition for an isotope. Now, for example, there are three different isotopes for carbon. All right, there is carbon 12, carbon 13, and carbon 14. All right, every isotope of carbon is going to have 6 protons and 6 electrons. All right, because every isotope of carbon has the same atomic number. All right, each one has 6 protons in its nucleus. That's what makes it a carbon atom. However, because we have different mass numbers here, we have different neutron counts. Carbon 12 has 6 neutrons, carbon 13 has 7 neutrons, and carbon 14 has 8 neutrons. And because each one of these elements have a different number of nucleons, a different number of particles present, they each have a different mass. Carbon 12 has a mass of 12.0000 AMU, which stands for atomic mass units. Carbon 13 has 13.0034 AMU, and carbon 14 has a mass of 14.0032 AMU. All right. Now, here's a puzzle. So there's 3 isotopes of carbon that occur in nature, right? 3 isotopes of carbon that are out there in the world that you can find. But if you look up carbon on the periodic table, there's only one mass written there, right? There's just one mass under C in the periodic table. And if at first you may be going, well, that's not that surprising to me, Josh. Like, I'm sure that probably that mass on the periodic table is probably an average, right? If we took an average of these 3 masses, that probably explains why there's only one mass present, right? Let's see. When you take an average, you add them all up, and you divide by the number of things, right? So let's do this. 12 plus 13.0034 plus 14 point. Oops. Oh, here. 12 plus 13.0034 plus 14.0032 divided by 3 is so average 13.0022 AMU. All right, this right here is the average mass of the 3 isotopes of carbon. But if you look it up on the periodic table, the periodic table says the mass of carbon is 12.01. What in the world is going on there? Now here's the thing, all right? The reason why the mass on the periodic table is 12.01 is because it's not a pure average. It's something called a weighted average. You see, on the periodic table, when we took an average of these 3 masses, we assumed that it was an even ratio, that the ratio of carbon 12 to 13 to 14 was 1 to 1 to 1. But it's not. There's something called natural abundance. Turns out in nature, 98, oops, 98.93% of all carbon atoms in nature are carbon-12. 1.07% of all carbon atoms found in nature are carbon-13. And 1 times 10 to the negative 10% atoms of all the carbon atoms found in nature are carbon-14. So the periodic table doesn't present you a pure average. It takes into account how much of each isotope is present in nature and then takes what is known as a weighted average. All right? So let's, at this point, learn how to use these natural abundances in conjunction with these masses to calculate the atomic mass of carbon, all right, or any element for that matter. So, couple things. So this type of problem, we are going to calculate the atomic mass which, if you're wondering what is the atomic mass, it's when you look something up on the periodic table, like carbon. The atomic mass is right here. All right, it's the number beneath the element on the periodic table. And to calculate the atomic mass, you need to know how to calculate something called a weighted average. All right, to calculate a weighted average, you need to take the first mass and multiply it by the natural abundance, the percentage, divided by 100, plus you take the mass of the second thing, multiply the mass of the second isotope by its percent abundance over 100, plus you go ... until you add the last thing, the mass of the nth thing, times its percent over 100. This is the equation for taking a weighted average. All right. So we're going to use this to calculate the atomic mass for carbon, and I'm going to issue our first buyer's beware of the week. I've definitely given caveat emptors before. This type of problem, if you're doing it and you're like, oh, this is horrible, but how likely is this going to show up in my future? This type of problem, calculate the atomic mass for, there is a 100% chance of it showing up on exam 1. It's already in the homework for this week, homework set number 2, which is based on chapter 3, and it will be on your first exam. So let that add a little bit of weight, not to make a pun, to this problem where we're about to work through it step by step, but pay attention, practice this. This is something that you want to get good at. All right, now let's use this equation to solve this problem. So we need to take the mass of each isotope, right, and multiply it by its natural abundance. So the mass of carbon-12 was 12.000 AMU. We need to multiply this by its percent abundance, which is 98.93 over 100. All right? We need to do the same for 13.0034 AMU. We take this, multiply it by its natural abundance over 100. We do the same thing for 14.0032. We multiply this by its percent abundance, which is 1 times 10 to the negative 12th. Sorry, 10th. Negative 10th. Put that over 100. All right, now we're going to take all these and add them together, right, at the end of the day. But first, we got to multiply these through. When you take 12.0000 times 98.93. Whoa, hang on. Oh, yeah. Times 98.93 divided by 100. This comes out to be, actually, I should bring it a little closer. $11.8716. But you have to ask yourself, how many sig figs can I keep? My 12.0000 has 2 non-zero digits, 1 0 at the end of the number to the right of the decimal, and then 3 in between. This is 6 sig figs, but my percentage, which is a measured quantity, only has 4. All right, so my answer can only have 1, 2, 3, 4, and 1 is going to round down. All right, so this 11.87 AMU is what I get. Let's do the next one. All right, so we have 13.0034 times 1.07 divided by 100. So here, this number comes out to be 0.13913638. How many sig figs can I keep? Well, my mass has 4 non-zeros and then 2 trapped between. That's 6 significant figures. But my percentage only has 3. So I can only keep 1, 2, 3. This 1 is going to round down. So 0.139 AMU. All right, finally, 14.0032 times 1 times 10 to the negative 10 divided by 100. This is going to give us 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 14003.2 as our product. How many sig figs can we keep? Our mass has 6 sig figs, but our percentage only has 1, so we can only keep 1 and 4 rounds down. So we leave that off. Whoops. Leave that off there. Brianna, great question. Sometimes Canvas can be a little rigid in the answers it accepts, but in this case, it's not. Canvas accepts both, fortunately. Okay, so we have now done our multiplication. It's time to add these numbers. All right, it's time to add these numbers. When we do, oops, here, let me punch that in, 11.87. The value that our calculator gives us is 12.009 then 7 zeros followed by a 1 AMU. All right, the question is, where do we round? All right, now we just did addition, so we have to look at the least precise number, whichever number has its last significant figure furthest to the right, and that falls to 11.87. We have to round to our answer to the second decimal place. 9 is going to round up, so when we do that, our answer rounds to 12.01 AMU, and this is our final answer. All right, this problem's hard on a couple levels. It involves changing from multiplication to addition, right? So there's rules for sig figs for multiplication that you have to apply, and then you have to add them, different set of sig figs. So that's a little tricky with this problem. It involves very long numbers sometimes, as we can see with our masses. Anyways, but this is the step-by-step on how you do the problem. You multiply the mass of every isotope by its percent abundance over 100, and then add all those together. That is your final answer. You're guaranteed to run into this in your second homework set on Canvas, and on exam 1, which, believe it or not, hits at the end of next week. So we're a week away, or 2 weeks-ish, in between a week and 2 weeks away from exam 1. All right. Okay. So that is where the atomic masses on the periodic table come from. They're a weighted average of each naturally occurring isotope that we can find in nature. Yes, Susan. Absolutely. You will absolutely be given the percent abundances. There's no reason why you'd have to memorize those. They're not from the periodic table. I will totally give those to you for every problem that you work. Okay. Cool. Okay, so now that we've talked about isotopes, where the atomic masses come from, let's spend a moment talking about the periodic table. All right, the periodic table. There's a couple things that we need to be aware of. First off, so on the periodic table, and actually I have it down here. So when you look at the periodic table, there's a couple different ways where we can break this up. So the first, well, before we start talking about breaking things up, let's talk about just a little bit of vernacular, so that we're familiar with how this thing works. So first off, the periodic table can be broken up into rows and columns. And when we talk about the columns of the periodic table, these are known as groups. All right, groups of element. Everything in the same column, every element in the same column belongs to the same group. So that's one way to look at the periodic table. Another way is you can look at rows, right? You can look at rows. Everything that's on the same row of the periodic table is said to be on the same period. All right, and the periods are numbered in succession. So we say that there's the first period, which is 1, 2, 3, 4. This one's the 5th, 6th, and 7th. All right. So those are the periods of the periodic table. You can say first period, second period, third period, and you're saying it's all the elements. You're referring to all the elements in that row. The groups have slightly different names. There's the A groups and the B groups, which I'm not going to get into, and you are not required to memorize. So, anyways, yes, you just need to know that the elements all in the same column are called groups. Now, the reason why the groupings of the periodic table are important, both the groups and the periods, they're both important for two different reasons. First, there's this concept called periodic law. All right, and periodic law is a very important concept, and it simply states that elements in the same group have similar chemical properties. All right, so we can expect that elements that all belong to the same group will behave similarly, react similarly. It's like being in a family. It's like, oh, well, people from that family, they kind of tend to be like this. And it doesn't mean that every single member of the family is exactly the same, but there's kind of a way of being that they all more or less adhere to. All right, and that is what periodic law says. You see these kind of repeating behavior patterns in atoms and elements, and those repeating behavior patterns are shared by elements within the same group. We'll learn a little bit more why that is a bit later. All right, now there's a couple different ways we can chop up the periodic table, and they're both important for different reasons. The first that I want to focus in on is, there we go. I want to talk about metals versus nonmetals. All right, metals versus nonmetals. Now, this is something that I do expect you to be able to identify. So if you're looking at a periodic table, you should be able to know what region are the metals in, what region are the nonmetals in, etc. And where you find that many periodic tables have this kind of illustrated for you. But if you don't have a periodic table, like I don't have a periodic table that shows the line, the dividing line between metals and nonmetals, it's right here between boron and aluminum. All right, that is the kind of dividing line. And if you stair step down the periodic table, this kind of track, these are the train tracks that divide the metals from the non-metals. All right, and this side of the periodic table over here, these are the let's see, I'm gonna go non-metals. Whoops. Are over here, and our metals are all over here, with the exception, all right, so you've got, well, give me a second. The metals are to the left of that dividing line, the nonmetals are to the right. Now, there's a special category of compound known as the metalloids, And the metalloids are kind of every element that touches that dividing line, all right? Basically, metals versus nonmetals, these are two categories that we've created, right, that humans have created. But it's not like there's a light switch where it's like, oh, all of a sudden it switches from metal to nonmetal. It's kind of a gradual gradient. And so these compounds these elements in the middle that kind of touch the line have some metallic property and some non-metallic properties, all right? These are known as the metalloids. All right. For example, metals conduct electricity. Non-metals don't. They insulate. Semiconductors are all metalloids. Semiconductors like silicon, like germanium, they're all in that range where they're kind of in between being metal and non-metal. All right. Now our non-metals are going to be all over here. All right, with one very notable exception. Hydrogen is also a non-metal. Hopefully that does not come as a shock to you. And our metals are going to be everything, everything on this side of the line, except for not including hydrogen. All right, so all these dudes in here are metals. And then all these dudes over here and way over here are our nonmetals. Hydrogen's not a metal, in case you were wondering. So that's one way you need to be able to look at the periodic table and kind of chop things up. Look for, again, by way of repetition, the train tracks start between boron and aluminum and move down if you have a periodic table that does not include this for you. All right, that's the dividing line between metals and non-metals. Everybody kind of close to that general region is called the metalloids. Then you've got the non-metals to the right and the metals to the left. All right, that's one way of breaking down the periodic table. Another way of breaking it down has to do with what we call blocks. All right. Now, you'll notice the periodic table kind of has a weird shape to it. You've got this zone over here. You've got this kind of, it drops down over there. Then it kind of rises back up here, and then you've got this other zone that's like super dropped down, right? Like right down there. Now, these are the 4 blocks of the periodic table, and they become very useful once we start doing electron configurations, which we will this chapter, probably even maybe tomorrow. Yeah, we're totally going to start doing electron configurations tomorrow. And so knowing these blocks will be useful. Here in yellow, this is known as the F block. Green is the P block. This kind of salmon color, this is known as the D block. And over here in blue, this is the S block. All right, so you have your S block, D block, P block, and F block. All right, these are kind of the general reasons of the periodic table. It's good to know them by blocks. It's good to know where your metals and nonmetals are. These are all things that you can be tested on. All right, let's see where we are. All right, it's 2:27. We have about 3 minutes left. I think I'm going to call this lecture here. I'm going to put a pin in it right here. We'll come back tomorrow and start talking about So today our focus has been kind of on the nucleus, on isotopes, on the nucleons. But then this discussion of the periodic table is setting us up to talk about the electronic structure of atoms. What are the electrons doing? We know the protons and neutrons are sitting there together. There's different numbers of them clumped up in different isotopes, but what are our electrons doing? And we will start kind of discussing, exploring the structure, the electronic structure of the atom, when we come back tomorrow. So this is the official end of our first lecture of week 2. And that being said, we still got a couple minutes. I'm totally down to hang for a little bit. So if you have other questions, like say if you're still there. We can totally hit up the extra credit question you have had. Yeah, totally. So what was your extra credit question? Okay, let's see. Question 7. Okay, let me take a look. Let's see, assignments. Oh, let's. There. There. Okay. Oh, wait, hang on. Oh, that's so weird. Okay. You know what's so funny? Is before this was totally showing up for me. So Susan, your thing is you've got missing answers in question 7. Before this was totally showing up for me. Now it's not. Hang on. Let's see. I'm just going to do a little bit of editing here. Okay, here, hang on. At first I thought, like Susan, I recommended, give Firefox a shot. Oh, but you know what's so funny? Is here I was in Chrome, and Chrome wasn't doing it for me, but here I can make this a little better. Oops. Okay. Okay, so it may be a browser thing because I was seeing earlier when Susan actually asked me a question. Asked me the same question on question 7. I was in Firefox and I could see it, but just now I was in what's it called? Chrome, and it wasn't there. But what I did is I edited the problem. I think what was wrong is in there I had placed images, but the images weren't coming up. But what I just did is I just wrote it in text, and now it should be visible to everyone. So say, and Susan, you should be able to check it out, and it should be good now. Okay, let's see. Okay, Brianna, that was for you too. Okay, it should be visible in everyone's browser. I just uploaded it, or I just edited it and saved it. I don't know if it'll be immediately available to you, but at some point later today, check it out. If it's still not visible, let me know. But it should be, question 7 should be good. Prathana, quick question. I may be just totally ignorant, but I have no idea what CHP stands for. How many CHP? Oh, maybe like what chapters? I believe everything in here is so the oh no. Extra credit 1 is all chapter 2 problems. I kind of tried to go with a like a density theme, just because I thought that this was really it's density is like the first chapters. Sorry. Okay, yes, it's chapter 2. Density is kind of the first real concept with which we can do word problems, and this class has a lot of word problems, that sort of thing. And so I feel like it's an important thing early on to kind of test how ready you are, and to give you a taste of where this class is going. So by the time we're done, you're going to look back on the density problems and think, oh my gosh, those were so easy. But at the time they're introduced, they're the hardest thing that we've encountered so far, because they're relatively early on in the course. So I wanted to kind of, and I mean, there's extra practice you can do in the text at the end, those homework problems that I assigned that aren't graded. But I wanted to kind of create an assignment that has a lot of density stuff in it to kind of give you an incentive to kind of explore this more, work a little harder, and earn some points along the way. So yeah, totally. Are there other questions? Other questions out there? Oh, Jen, fire away. Let's see. Do I get notified or see your comments on previous lecture videos? I believe YouTube does send notifications when someone comments on a video. I'm not on YouTube a ton outside of class, believe it or not. So if you have a question with respect to something from lecture, and you're hoping for a response, definitely the way to go is either email or Canvas DM. Just because because I those are the best if you're asking a question and need a response. Excuse me, those are the two that I kind of check often and religiously. I casually look at the YouTube stuff, but it's mostly because I'm not really a proper YouTuber. Like, this isn't my bread and butter. So anyways, if you have a question and you need... Oh, okay. You're rewatching the lectures this weekend. Notice that we all missed a small detail. Also recommended to watch... Oh, nice. I've started Solar Opposites. I haven't finished it yet. It's definitely something that it's like, okay, this will help carry us through till season 4 drops on Hulu, because that's how I watch my TV. Okay, there's a detail that I missed. I will check out the comment and see what that is, and possibly correct it in a comment in a future video. Okay, let's see. Prarthana, will we be able to know what answers we did wrong after quizzes? I have to check the parameters, because there's this whole thing in Canvas where it controls like how much each student sees, etc. For the lab quizzes, the restriction's a little touch and go, just because those quizzes are shared between the other courses. So I'd have to get on the same page with the other lab instructors to talk about how much to show. So those are restricted just because it's content shared between courses, and I think there's some concern about like leaking answers, etc. For the I believe the homework sets should show. I can't remember. Every one is a different kind of parameter. So some you'll be able to see, some you won't be able to see. What went wrong? It's part of the one of the downsides to the online instruction is there's a heightened concern for exam integrity and security because of the fact that when I'm teaching a class, we all show up, we're in a room, I give you a test, you take it. I know nobody's proliferating answers because it's all within closed exam context, and online things are a little different. So it's the long convoluted answer to your question, Prarthana, is for some of them you will be, for others you won't, and it's just part of the nature of living this online life. All right, Esther. Let's see. Are the current lab quiz grades in Canvas pending? Okay. Great question. This was actually a question that I got. Let me actually make a note to myself. Esther, that is an excellent question. I'm making a note to include the answer in a post to the class. Okay. Okay, so Esther, excellent question. So for the oops. Wait, no. Go away. For the lab quizzes, the grade that is displayed when you finish taking the lab quiz, your grade, or I should say, the immediate grade gives a 0 for all free response questions. All right, the immediate grade gives a 0 for all free response questions, mostly because Canvas has no way to grade that thing. It has no idea how to, because it doesn't understand things, right? It doesn't understand the question that I asked. It doesn't understand the logic or lack of logic in the answers that you give. So, so that immediate grade that you see displayed is the grade that you get if you get a 0 on every free response question. Now, that doesn't mean you're going to get a 0 on every free response question. After the due date, I go back and grade the free response questions. At which point I'll post an update letting you know, okay, lab exercise 1 and 2, or lab quiz 1 plus 2 is graded now. And that way you'll know, like, oh, okay. And at that point you'll see your score, including what you scored on the free response questions. And yeah, so right now it doesn't, but I wait to grade them till everybody's answers are in, and once that happens, I go back and grade them and manually adjust the scores. So if you're looking at it and you're like, holy moly, I did way worse than I thought I did, it's got a 0 right now entered for your free response. I'll be grading those with my own eyeballs and assigning points accordingly, so you'll be seeing a bump in those sometime, probably sometime this next week. Again, the lab quiz is due tomorrow, so the earliest I could possibly get to these are on Wednesday. All right, so that's Esther's. Parthana, let's see. Homework sets show prereq exam. The prereq exam does not, because it's a test. So so that one doesn't show. Brianna, you're wondering the same thing. Do you go in and grade our Yes, I personally go in and grade the short answers. Will you let us know when the prereq exam grades are changed? Oh, okay, yes. Karenessa, I totally will. I totally will. Yeah, I haven't. So several people have emailed me about typos in the prereq exam. I'm going to be looking into every single individual case, and I actually use the statistical analysis for that Canvas provides to hunt for even some that maybe students haven't spotted. For example, it gives me the percentage of the failure percentage rate on each individual question, and whenever I see a question with a percentage rate that's tanked, I check it out, because I'm like, either that was a really hard question, which those are out there, or that's a question that maybe had no right answer because of a typo. And if a typo is there, then everybody who encountered it will be getting full credit on it, because it's not your mistake, it's mine. So I will be looking into every emailed instance, every emailed inquiry about typos. In addition, I'll be using the statistical analysis from the prereq exam to hunt and find ones that maybe even you missed. How will you know what you did wrong? Right. It's honestly, it's so actually this is a bit of a question that I have for you all, because I see things with my professor glasses on, like when I'm on the website, etc. Does it tell you, Parthana, does it tell you which problems you got wrong? Would be my question. Like, I know it doesn't display the answers, but can you like go back and look and see like, oh, I got this one right, this one wrong, this one right, this one wrong? That would be my question. Let's see. No. Okay. Let me. Let me do some tinkering in Canvas. Let me see if there's a way where I can make Canvas display the problems that were incorrect without giving the answers per se. Let me do some messing with Canvas parameters. I'll get back to you on that, because I totally understand wanting to use the exams as a study tool, and knowing what you're getting wrong is an important part of learning, because that tells you where to focus. And so if you don't know that, then you have no way of knowing or self-improving. So let me see how flexible or rigid Canvas can be. And I'll let you know what I turn up. But that's not going to be like a quick like, oh, let me just tap it in. That's going to take a little more digging. I read a lot of Canvas forums these days to see what all is available to me and to you. Totally, yeah. Are there any other questions before we go? Or before I go? Well, I guess we'll all be going. When it's your time to go, it's your time to go, right? All right, well, if there are no further questions, then I will call this lecture here. Thank you, everyone, for dropping by, asking awesome questions. Tomorrow we'll have not only lecture, but we'll have our lab office hours. Your last chance to get those questions answered before the midnight due date of Lab 1 and 2. Okay, double checking. Unknown solution from Lab 2 is calculated. That is correct, Esther. That is... Oops. That is 100% correct. I just have to say, too, I trip a little bit, Esther, every time I see your handle in the comments section, because my sister-in-law is named Esther, and her last name also begins with S. So I'm like, every time I see your name, I'm like, wait, Esther? Why is my sister-in-law taking my chemistry class? Anyways, one of life's fun little coincidences. So yeah, you calculate the unknown solution from Lab 2 using... Oh, sorry. You said, is it calculated or... And I just said, yup. I should get better at reading the full question. Sorry. No, it's not an estimated thing. And you calculate it. Using the density of the unknown and the equation of the line. From your graph. Oh, Peter, you rock. You are the one who rocks here. Thank you for the kind words. Alrighty. So that'll be all for today. I hope you all have a totally. I hope you all have a happy Monday. And I'll catch you all back same time tomorrow. And then office hours after that. Later.